Okay. Today we are going to look at discrete math. Now, this is still on what? The series on mathematics. The first class in this series was what? Threshold. I taught you threshold. Now I will explain why I had to teach you that first in this class. So this class is discrete math. But before I continue, let me explain something to you. I am teaching mathematics in relation to machines, not mathematics in relation to human being. Now, mathematics in relation to human being, mathematics is treated as a pointer to the source. But mathematics in relation to machines, mathematics is the source. That is the origin of the law that flows down to physics and engineering, right? So it is on that basis I'm teaching mathematics in relation to machine. Mathematics is the source. I had to tell you this in order for us not to drift into idolatry where we collapse meaning into symbols. I don't want that to happen. So I don't want you to start this conflicting argument about what you believe or what you don't believe, right? So let's leave that aside. All right. So today I'm going to teach you discrete mathematics, and in doing this, I'm going to look at 4 different topics in this module. But probably this class will just allow us to take 2. So the first one will be what? 1, Boolean algebra. And then the second one is what? Binary state. And then the third one is what? Truth tables. Then the fourth one is what? Switch theory. Okay, these are the 4 topics I'm going to teach under discrete math. Now, why do we have to do this discrete math? Reality is continuous, but machine is not, right? Um, when you look at things like temperature, you look at things like sound, right? It varies smoothly, but machines has to decide, and that decision requires boundary. That boundary is what we consider as threshold in our first class. You know, in the first class, I told you we are having something like this, like this. So let's consider this as 0.3 volt, right? This one as 0.7 volt. Now, when you cross this, so this is 1, this is 0. So we are having all this inside. So this one is considered as what? Noise, right? So this is the threshold. This is the threshold. So once voltage is rising from 0 and it gets to 0.3, it will become, the transistor will switch to 1. When the voltage is coming down, it crosses this 0.7 until it gets to 0.3. It will still remain as 1. Then when it crosses 0.3, it will become what? 0. So this is the method through which you convert that uh, continuous reality to what? To two-state environment, which is what? 0 or 1. And that state, 0 or 1, is what you look at as what? Binary state. So how do we achieve 0 and 1 in an analog system? Through the concept of what? Threshold. Right? That was why I taught you threshold in that class. So that is what enables us to achieve 0 and 1 from analog system, from a continuous reality, where you bring in voltage to the circuit. An electric field is generated instantly, producing magnetic field, and then causing energy to flow from the source to the destination. So discrete mathematics, looking at Boolean algebra and binary state. So we are going to look at these two now. We're going to look at this one. So this is looking at off, on, right? High, low, high. No, yes, right? False, true. That is what this does. Binary state is just two states, 0 or 1. That is what this is dealing with. Now, if you look at these two, they look similar. You are looking at on, off, on, low, high, no, yes, false, true, then 0, 1. Same thing. Then, if that is the case, why do we have these two under discrete mathematics? That is because both are operating at two different layers of the system. This one is operating at what? Logical state, the logical layer, right? This one is operating at what? The physical layer. So, which is what we call physics, right? Now, we need these two in machine design and in their operation because at the logical layer, this Boolean algebra, at the logical layer, logic does not see uncertainty. Uncertainty is the smooth growth of the voltage from 0 to 0.7. That is uncertainty, right? So logic does not see that. So physics has to convert that uncertainty into what? Certainty, which is 0 and 1, which is a finite state. So that has to be converted to 0 and 1 before it is fed into what? This Boolean algebra. So what does this do? This has to do with what? Condition evaluation. Condition evaluation. So we are checking if the two conditions are true or not. Then what will be the output, or what are we going to do? That is what we are doing. So it's not measuring value, it's testing, it's evaluating the condition. So to achieve this, we use and, right? Or and not. These are not just the three. There are more, but these are the three we'll just focus on. So if we now say that, and again, another thing I want you to get in these two is that you must consider two operational concepts. Otherwise, there's a paradox here. The chicken and the hen. Which one came first? To understand that, we have to look at two operational processes. First, when the engineers are designing the machine, which one is first? Boolean algebra will come first, then binary state. But when the machine is operational, that is running, which one comes first? Binary state before Boolean algebra. So binary state becomes an input to Boolean algebra, meaning the electrons, the electricity flow, which is what? The voltage has to be converted to what? To a certainty state, which is 0 and 1, before it is now fed into Boolean algebra, in which decision has to be taken. So we can now say if, right, voltage is greater than threshold, right, and clock equals high, right, then execute. So this is it. So before you can get to this Boolean algebra, which is this and evaluating the conditions, you need to have the state already. So voltage, looking at, we can say 0 to 0.3, or we say 0 to 0 volt to 0.3 volt, right, is considered as 0, while 7, 0.7 volt, right, to 5 volt is considered as 1. Now, the threshold is now in between, which is what? From the 0.3 to 0.7. So this is the threshold. This is what now guides the switching from that continuous state into 0 and 1 and 0 and 1. So I explained in the threshold class that once it is below 0.3, the transistor switches to 0. Once it is above 0.7, transistor switches to 1. But I also explained the concept of hysteresis that guides what is in between, which is the threshold, right? How the state is maintained as 0 or 1. So you have to watch that video on threshold to understand that. So these are the two discrete maths that I want to teach you in this class: Boolean algebra and binary state. Boolean algebra is dealing with on, off, low, high, no, yes, false, true. So you are looking at condition evaluation and you are looking at this operation. So these are the tools. And, or, so if this condition is true, if voltage is greater than threshold, that becomes 1, right? Then clock equals to I, that becomes 1. So we are going to execute. So the output will be what? 1. But if voltage is not greater than threshold, that is 0. Even if clock is high, that will still give you output 0. So it's evaluating the state in order to take that decision. That is why I am showing you Boolean algebra and binary state. So first, physics has to convert uncertainty to certainty, which is convert the smooth flow of voltage to what? 0 or 1, using the concept of threshold, before a decision can now be taken by evaluating those states. So that is what I want to show you in this class. Binary state is what remains after ambiguity is removed. Continuous flow has ambiguity. It will confuse the transistor to switch. So once that ambiguity is removed, what remains is binary state. And to do that, you have to use threshold. I've explained. So that is what I want to show you in this class. So in the next class, I will show you the truth table and what? The switch theory. So the truth table has to do with this on-off and then this algebra, linear Boolean algebra. What happens when it is and, when it is or, and when it is not. So till we see in the next class. Bye-bye.